Stop button. No. I don't need to. Okay. Yeah. Yes. Yes. Good morning, class. Today, we're starting a segment, General Physics 3, Behavior of Matter. And my name, as displayed on the screen, Professor Emmanuel Aribi of Department of Physics and Engineering Physics. Well, I didn't put my email address there, but I think in the other one, maybe I'll make it available. The topics of interest that I'll be looking at today, we're looking at hydrostatics, hydro, talking about fluids, statics, their motion. So in that context, we'll be looking at pressure, buoyancy, Archimedes principles, and then we'll go ahead to look at Bernoulli's equation. Then we'll also discuss incompressible fluid flow. Then we'll take a look also at surface tension, talking about adhesion, cohesion, viscosity, capillarity, drops, and bubbles. Our reference text is Fundamentals of Physics by Halliday, Resnick and Walker, the 10th edition. Actually, you can get this in soft copy and also in hard copy. You can do well to actually get yourself a copy so that you'll be able to follow us as we go along in this lecture. Fluid density and pressure. Before now, these topics, we are all familiar with them. And ordinary level physics, talking about fluids, density, and then pressure. We know that these form the basis of hydraulic engineering, a branch of engineering that is applied in many great fields. For example, we look at fluid flow in the hydraulic system of an aging nuclear reactor. We also look at blood flow in the arteries of an aging patient. That is concept that we are talking about is applicable also in blood flow. Humans looking at the arteries of an aging patient. Also, if you are interested in looking at the drainage from waste sites or the efficient irrigation of farmlands, these are areas of applications to which our knowledge of fluids becomes very, very essential. We do well to actually understand these areas. Just imagine hydraulic system actually avail us the opportunity to even do work from your O-level experience. Talk of the hydraulic jack, in which case you apply a smaller force to actually carry a bigger load. Take, for example, the jack that you use for your car. Can you carry the car up? The car that is maybe of average size of or average weight of 400 kilograms, you cannot carry it. Your own weight is just 60 kg, or even if you are very hefty, maybe 80 kg. But with your weight, even if your weight is 40 kg, you apply the hydraulic press, hydraulic jack, to actually lift a car as big as 400 kilograms, just by applying a force, and then you are able to carry that big load. In fact, there are new systems that uses electric system, still hydraulic. You just punch the thing goes up. This is very, very important. So we come to the question, what is a fluid? Before now, we've talked about liquid, gases, and solids. even from chemistry understanding. But in physics, and in trying to look at physical phenomena, whether natural or artificial, a fluid actually, in contrast to a solid, can actually flow. And we know that fluids conform to the boundaries of any container in which we put them. We know that liquid and gases are examples of fluids. We'll look at density. With fluids, we are more interested in the extended substance and in properties that can vary from point to point in that substance. That is, we look at a continuum. Unlike when I'm looking at a solid, solid is compact, I can weigh it, but for fluid, we can also weigh it, but it will be a kind of, that's the way we do that when we are looking at, say, the weight or the volume occupied by fluids. So it is more useful to speak of density and pressure than of mass and force when we are talking of fluids. Density. To find the density rho of a fluid, we are used to that symbol rho. To find the density rho of a fluid at any point, we actually isolate a small volume element V around that point and measure the mass M of the fluid contained within that element. And we can just say, okay, for this fluid, the density is just the ratio of the infinitesimal change in mass to that of infinitesimal change in volume. So that in practice, we assume that a fluid sample is large relative to atomic dimension, and so is smooth with uniform density. This assumption allows us to write the density of mass and volume of the sample. And then we can write for uniform density that rho is actually mass over volume. And in physics, the SI unit is very important. And from that expression, you can see mass in kilogram, and then the volume in meter cube, so that the SI unit for density is kilogram per meter cube, per cubic meter, or Then I'm interested in this table, and you should also be interested in it. The table actually shows the density of some substances and the average density of some objects. Note that the density of a gas varies considerably with pressure, but the density of a liquid does not. Density of a gas varies with pressure, but the density of a liquid does not. This suggests that gases are readily compressible, but liquids are not. So let's look at material objects and density in kilogram per meter cube. Interstellar space. I told you what we are trying to look at is actually broader, okay? Because this is a foundational course actually for some of you that will venture into some other areas of study. Actually, those of you in tech, those of you in computing and engineering, and those of you in physical sciences and the likes. Interstellar space. What do we call interstellar space? That is between bodies in space. From your geography, O level, or your rudimentary geography, in our solar system, we have many planets. It used to be 9, but now 8, excluding Pluto, who by definition does not make that of a planet. So, interstellar space, there are density variations there. That is between one object in space and other objects in space. Take, for example, our Earth and then the Mars, or our Earth and then the Sun, and many other heavenly bodies that we can actually mention. So the density in that case is 10 to the minus 20 kilogram per meter cube. Take note of that. And then again, air. We said air varies, with pressure. That at 20 degrees C and 1 atmospheric pressure, in the course of this lecture, you get to know what we mean by atmospheric pressure. It's what you know before now. Just 760 mmHg. So 20 degrees C and 1 atmospheric pressure, the density is 1.21 kilogram per meter cube. The same air, the same temperature, but at 50 atmosphere, that pressure is 60.5 kilogram per meter cube. And of course, we have styrofoam having a density of 1 times 10 raised to 2 kilogram per meter cube. Ice, the density of ice is much, 0.917 times 10 raised to 3 kilogram per meter cube. Then let's look at air and water now. Just like stated before, we look at the same variation. You see that air, there's a marked variation, a remarkable one. But if you look at water, say at the same temperature of 20 degrees C and 1 atmosphere, it is just 0.998 times 10 to the 3 kilogram per meter cube. But same water at same temperature, 20 degrees C, and at 50 atmosphere, you can see there's not a marked change, not a remarkable change. It's just 1 times 10 raised to 3 kilogram per meter cube. But if you look at seawater, 20 degrees C, and at 1 atmosphere, it's 1.024 times 10 raised to 3 kilogram per meter cube. We can see that when we are doing calculation of that quantity of heat, water, no matter what, whether it's in ice form, look at the one for ice, look at the one for water at 20 degrees C, or at 20 degrees C, and seawater at 20 degrees C, you can see that all of them is around 1 times 10 raised to 3 kilogram per meter cube. So we are very safe or conveniently okay to say that the density for water, whether ice, whether seawater, is approximately 1 times 10 raised to 3 kilogram per meter cube. You can see that clearly on that table. The table is very important. Then if you look at for blood, you can see that it's also very close to that of water. Sorry, can I wait? Please give me a moment, please. Sorry for that interregnum, for that interlude. My apology, please. Okay. Okay. So for blood also, you can see that the density is also very close to that of water. What does that suggest to all of us? That goes to show that blood by density is very close to that of water. Can you see that on that table? Approximately close to that of water. That suggests that our blood system contains a lot of water actually. So that's that one. Then for iron, you can see that density is 7.9 times 10 raised to 3 kilogram per meter cube. For mercury, that is not Mercury planet, but the metal, it's also 13.6 times 10 raised to 3. Earth, 5.5 times 10 raised to 3. The core of the earth is also 10 raised to 3. Crust is also 10 raised to 3. So you can see that essentially all of these are 10 raised to 3. The sun, likewise, the white dwarf, they are special star, So that's also, that is suggesting that they are very dense. That's in the space. Uranium, 10 raised to 17. And neutron star, another type of star, 10 raised to 18. Our sun is also a star. Okay? So you can see that this density variation are of interest to us. We can take attendance now. Code 1. Are you listening? How many people here? Okay. Just one. Okay. So you can take the code 1, 7Y, 3WL. Let me take that again. Code 1 for attendance, 7Y, 3WL. Okay. So let's go on to pressure. Look at density. Let's look at pressure also. For us to understand pressure, let's look at the density, the pressure from the viewpoint of what you know before now. You know what we call a piston when we are talking of four-stroke system, talking of ignition, compression, combustion, then exhaustion. We've come across that before now. So just imagine that piston is cylindrical in shape, and you have something with which you can just press the gas in the piston down. So if you have a pressure, if you apply a pressure, that is force over the area, the force you're applying is F, then over an area A. So we get the expression for pressure as shown in the slides above. That is infinitesimal change in F over that of infinitesimal change in area. However, if the force is uniform over a flat area and evenly distributed over every point of the area, so we can write the pressure F as a pressure P as F over A. Okay? Where F is the magnitude of the normal force on area A. And by experiments, we find that at a given point in the fluid at rest, the pressure P has the same value in all different directions at a given depth. That is, at a given depth, maybe in a fluid or maybe in a liquid or a swimming pool, imagine a diver or somebody at a particular depth, the pressure on that point is the same in all different directions at that depth. And of course, we know pressure is a scalar, and so it has no directional properties. it has unit of Pascal or Newton per square meter. And we know that 1 atmosphere, though I mentioned it earlier, is just 1.01 times 10 to the 5 Pascal. And that is 760 Torricelli. That is after an Italian, Torricelli, Evangelista Torricelli. And also, you can measure it also as 14.7 pounds per inch square. That's more of a British system. So what are the units by which you measure pressure now? So that you have it in atmosphere. For example, I can talk of 3 atmosphere. 3 atmosphere. We know the meaning now. Or if I want to convert it to Pascal, it will be 3 times 1.01 times 10 to the 5 Pascal. And it's also 760 Torricelli. That will be 3 times, that is for example now, it will just be 3 times 760 Torricelli units. Or 3 of that, or the right conversion in pounds, that's pounds, LB, pounds per inch squared. The atmosphere or ATM is the name, is as the name suggests, the approximate average pressure of the atmosphere at sea level. That is at sea level. That is the approximate average pressure of the atmosphere at sea level. And then, of course, Evangelista Torricelli, which we call millimeter mercury. You can see now, instead of saying 760 Torricelli, you can just put 760 mmHg. It's the same thing. And then, of course, the pound per square inch is often abbreviated as PSI. PSI. If you look at your tire is measured in PSI. So just go to the vulcanizer and say, I want to measure my tire. Okay, what is it? You say, it's 40. Measure 40. It's 40 PSI. Okay? So you can actually convert that to, that's in British units. So we are all using the British unit without knowing, in a way. That's why, as somebody who will be in the area of fluid mechanics or who want to work in that area in the course of your course or program, you must know that psi or PSI is actually a unit of pressure, and that is convertible by what you have there. So you must know this. It's very important, because actually in this course we are looking at pressure critically. Very, very important. So let's look at this table. We want to look at pressure. We've decided to use the unit of Pascal for all of them. The center of the sun. What's the pressure at the center of the sun? You'll be wondering, how come we're able to determine the center of the sun? It is very possible. From theoretical consideration, we can actually infer or get to know what the pressure at the center of the sun will be, just purely from theoretical consideration, because the surface of the sun is very, very hot. There is no instrument you can take near the surface of the sun. Even the closest of the telescope or observing systems that can look at the sun are some astronomical units away. When I say astronomical units, I'm actually saying 10 times 10 raised to 10 meters away. It can be 20 astronomical units. That's 20 times 10 raised to 10. 20 times 10 raised to 10 times 1.5. because 1 astronomical unit is 1.5 times 10 raised to 10 meter. That's the distance. But by theoretical way or theoretical means, we can actually determine what the center of the sun's pressure will be. And from such, we are able to get to know that the pressure at the center of the sun is actually 2 times 10 raised to 16 Pascal. Center of the earth, the pressure of the center of the earth is 4 times 10 raised to 11 Pascal. And then in the sustained laboratory pressure that is possible, we're able to get up to 1.5 times 10 raised to 10 Pascal. Then, of course, deepest ocean trench, that is at the bottom of a trench of the ocean. The pressure there is also much. 1.1 times 10 raised to 8 Pascal. Then, interestingly, the spike hill or the dance floor. I don't know that you have seen people that are into, I don't know the name of this dance now, that they normally have high heel. The pressure due to that spike heel on the dance floor is 10 raised to 6. So it's much. Then the pressure in an automobile tire is also 2 times 10 raised to 5 Pascal. You can get that and convert that to psi if you decide to check that. Okay? You can try to check that and get to know. Then the atmosphere at sea level. At sea level is 1 times 10 raised to 5. Then normal blood systolic pressure is 1.6 times 10 raised to 4 Pascal. Then for a vacuum, laboratory vacuum that is possible, we have 10 to the minus 12 Pascal. So these are some of the things we need to know about density, pressure, as it applies to fluids. And then you should take note of some of the things on this table of air, same temperature, different pressure, and there's a remarkable difference. But water, same temperature, different pressure, is about the same. These are facts we must know. And then for blood also, the pressure in the human blood is also about that of water, and it's about that of water. So these are facts we must know. So that table says many things. So you should take cognizance of that and get to know some of this in the course of this lecture. So the next one is for us to look at example. So if I were you, I'll take my pen and paper and try to look at this example. If you look at in this example, we have a living room with having floor dimensions 3.5 and 4.2 and a height of 2.4 meters. So the volume in that case is length, breadth, and then the height. We assume the dimension of such a room is uniform. Many rooms may not be uniform. Like in the room where I am now, it is not uniform. The height may be the same, but the length and breadth may not be the same. So the question now is, what does the air in the room weigh when the air pressure is 1 atmosphere? See, you are now giving something in atmosphere. And you know 1 atmosphere is 760 Torricelli or 760 mmHg. I know from 760 mmHg, what will you do? You need to convert that to Newton per meter squared because your volume is given in terms of meters. Okay? So, what are the things we have to do in this particular question? The weight is mg. M is its mass. We should know that. And we know that M is related to air density rho and the air volume V. Just like I said, we want to know what is the mass. In this case, we know that density is mass per volume. So if I get the mass will just be density times volume. But I'm interested in knowing the weight of air, which is something about. So once I get the mass of air, which is rho v, I can get the weight, because weight will just be what? Mass times g. That's what we have there. So the mass is 420 Newton. Were you able to get that? So let's take our time to look at the next code. Attendance code. Attendance code number 2. Attendance code number 2. Attendance code number 2. J 8. Sorry, J, this is B, is B. J, B, V, P, E. Please, let's take that again. Let's take the attendance again. The attendance code, let's take it again. J8 V P E. Let me take that again. J8 V P E. That's attendance code number 2. So we continue. We now know the weight of air when the air pressure is 1 atmosphere. Just like I said, convert that. We'll need that in our yes. So we have rho, the volume, and then G. Okay. Second part of that question is, what is the magnitude of the atmosphere? Downward force on top of your head. That is, as we are down, there is a pressure due to the atmosphere on top of our head. Assuming our head has an area of 0.040 meters squared. Okay. In this particular calculation, they just use the atmospheric pressure the way it is. But if you choose to, you can convert. You can see the way it has been converted here. 1 atmosphere is that. So 1 atmosphere will just be 1 times that over. That's what they have done in the calculation you see. I don't know whether you see the calculation. The B part, that's on the right-hand side of that example. On the right-hand side of that example, I hope you can see it. That's why you have that conversion. That is, the force will just be pressure and area, because you know by definition, pressure is force per area. Pressure is force per area. Pressure is force per area, so that force will be pressure times area. So you can see the calculation they are doing there. You should not confuse you. Just like we normally do conversion. we say 1 atmosphere is 1.01 times 10 raised to 5 Newton per meter squared. But in this particular question also, what we are interested in is also 1 atmosphere. So 1 atmosphere will now be 1 times 1.01 times 10 raised to 5 Newton per meter squared divided by 1 atmosphere. But if it were to be 2 atmosphere that we are given, if it were to be 2 atmosphere that we are given in that question, what are we going to do? What we just need to do, we just to say 1 atmosphere is equal to 1.01 times 10 raised to 5 Newton per meter squared. So 2 atmosphere will just be 2 times 1.01 times 10 raised to 5 Newton per meter squared divided by 1. I hope you get what I'm trying to say. So that the force in this case will just be 4 times 10 raised to 3 Newton. So you can see that there's a pressure actually on top of us. That's what that question is saying. So this large force is equal to the weight of the air column from the top of your head to the top of the atmosphere. So you can see that we need a lot of energy eating. We need to eat to have energy actually to be able to move. To be able to move. And so, if you remember, during your own level, you must have done a calculation in which, if you know the height, if you want to know the height of a mountain, for example, what you need to do is just to take the pressure at one point and take the pressure at another point. Once you know the pressure at the 2 points, you can actually get to know the height of that mountain or the height of that building. As a scientist, you should be able to. Take, for example, if you get to a building, very high-rise building, and you are with a barometer, and you want to know the height of that building, you can. What do? With your barometer at the base of that building, take your measurement. In which case, we will assume that you place your measurement on the ground floor, not that you are holding it. If you are holding it, you will have covered some distance, maybe a meter or 0.0 meter, depending on your height. So if you take the barometer reading and you take the barometer reading up, that can give you the height of that building. That can give you the height of the building. And of course, this question is also telling us that as we go up, the pressure reduces. Okay? Because we are here, the pressure on us is much. Something 10 raised to 3 Newton. That's the force of that pressure. I don't know whether you watch a man widely reported just about a day or 2 days ago. A climber, American climber. He was able to climb Taipei 101 without any rope. Without any rope. Very young man was able to climb one tall building in Taipei. That's capital of Taiwan. Was able to climb up to that level. So that man must be doing a lot of work against gravity. And of course, must be experiencing a reducing pressure or reducing force. But he was able to summon that courage and he was able to get that done. It was a great feat indeed. So we'll be looking at fluid at rest. I don't know whether we should. Okay, let's start it anyway. But our time is almost up. I don't know if you have any question. So before before we entertain last question, let's take the last attendance code. You are 99 online. I can see 99 people. So let's take our attendance. AW, AWD, PP, AWD, PP. Have you taken that? AWD, PP. That's our next attendance code. And that's the last attendance code. You can submit your attendance. You can submit your attendance for record purposes. Submit your attendance for record purposes. I don't know whether you have questions to ask. Question to ask? Or I don't know whether the system permits me to see if anybody is raising their hands. Here. Yes. Top chat, okay. So if you have questions, I'm waiting to receive your questions on what we have discussed so far. Your questions are welcome. No. So I want to believe that all that we have done are well understood by all of us. So let me ask you this question now. Just ask yourself, what are the various units by which we know pressure to be? In this class, can you tell me the various units by which we know we can measure pressure? The various units by which we know or we can measure pressure. And the SI unit for density, SI unit for pressure are things you should now know. And then you should take cognizance also of objects or materials and their density, and take particular recognition of air and then water. I mean, these are fluid that air at same temperature but different pressure. There is a remarkable variation in density. I also note that for water, same temperature and at different atmospheric pressure, the density variation is not much, as we can see on that table. And then, of course, the following have similar pressure. You must know the ones that have similar pressure on this table: ice, water, seawater, blood. All of them, they have density of about 1 times 10 raised to 3 kilogram per meter cube. That is ice, water, seawater, whole blood. They have a very similar density variation. And then, of course, the densest of them all is the uranium nucleus or neutron star. Neutron star is the densest of them all, with a density of 10 raised to 18. 10 raised to 18 kilogram per meter cube. So we should take note of all this. And with the examples that we have done today, I want to still looking up for your questions. No question? So I think we are done for today. And hopefully on Wednesday, we continue with our lecture, looking at fluids at rest. Thank you very much. I don't know if any of you may want to know my email address. I thought I have it in the slides. Maybe it's in the other one that I prepared. That is, if you have any question for me, you can write me an email at E from the word Emmanuel, EREB at OAU.edu.ng. Let me take that again. Email address EREB@OAU.edu.ng. Thank you very much for listening. See you at the next class. Thank you. Yeah. Yes. Wonderful. And concurrent viewers. Okay. Okay. On that. Okay.